just setting up the recording. I notice my phone is, oh shoot, it's actually dying. I wanted to record myself. Does anyone have a USB cable I could borrow to plug it into my laptop? I'm just kidding, guys. So wouldn't it be great if we had a world without USB cables? Okay, let's, yeah, so my phone is fully charged. But yes, maybe one day I'd be able to just kind of charge it without using a USB cable also. So I will talk to you today about technology which allows us to transfer electrical energy without using direct connections. Wireless power transfer via coupled resonators is not a new idea. In fact, it was pioneered over 100 years ago by this guy. Oh, I'm already moving forward with the slides. I'm sorry about that. I never even looked backwards. I think you guys are like, where's the slides? It worked just a moment ago. I guess I can mirror. Is the projector even on? No. Because actually my Mac detects that there is another screen.
Can you press HDMI on the control panel?
Let me look. Okay. So this is the title of my talk. Sorry about that. Rough start. Wireless power transfer via coupled resonators. It's not a new idea. It was pioneered by this guy who's very famous for developing a lightning machine. That's right, Nikola Tesla. So this guy used to demonstrate wireless power by holding a fluorescent light bulb in the presence of his Tesla coil and lighting it up without wires. And he had this really great idea to use a big Tesla coil and do this for the entire Earth. So this would ultimately do away with our wired power grid. His idea led to the construction of the Wardenclyffe Tower, which unfortunately was never finished due to funding, and so he wasn't able to demonstrate his scheme for transmitting power across the Atlantic Ocean. I was very interested in Tesla's schemes in high school, even though they didn't work out. So I decided to build a Tesla coil of my own and was able to transmit power from the sender here to the receiver coil and light up a 40-watt light bulb over about 6 feet, which is kind of depressing when you consider that I'm pushing about a kilowatt into this coil. So it's this sort of inefficiency that makes wireless power transfer such a challenge and probably explains why the only devices we have commercially using wireless power transfer are these chargers for phones and electric toothbrushes. The basic idea of wireless power transfer in the way I will present it today, there are other schemes as well, but this scheme involves, it's founded on the basis of magnetic induction. So Joanne already mentioned quite a bit of this in her talk, that an oscillating current in one coil can induce an oscillating current in a second coil. And this is what we call magnetic inductance. I'll be talking about two papers today, which both mark recent progress in this field and show kind of a renewed interest since the days of Tesla. The first one, called Wireless Power Transfer via Strongly Coupled Magnetic Resonances, is written by these guys who I'll call authors number one. It was published these people are based at MIT, and they managed to publish the results in the prestigious journal Science in July 2007. Their setup looks something like this. Again, we have a source coil and a device coil. And this is separation here is about 6 feet. Sorry, it's a little bit dim. And what I want you to notice is that the source coil and device coil are both open-ended coils. So they're actually not even closed loops. They hang freely in space like this. The source coil is excited by a one-loop resonator. And then it transmits its energy through a coupling kappa to the device side of things, where the energy is again picked up inductively in this one single loop, which lights the bulb. In terms of a circuit diagram, we can split this into two parts again, and both of these you will see are L RC circuits. Right? The only difference between this side and this side is that on the source side we have this driving term, F of t, and on the device side we have an additional form of energy which gets used in the load resistor. So if we write out the coupled mode theory equations, this is a way of describing how this system will work. We can relate the time derivative of the currents in these two coils to, first of all, a linear term in each one. For the first term here is imaginary. The first coefficient is imaginary, describing oscillations in the circuit. And the second term is a real part which gives rise to a decaying exponential form of the current. At this point, they're still uncoupled until we come to the second term, which mixes the two currents with an imaginary coefficient and a coupling kappa. And the last term describes that forcing in the source circuit. Of course, we as physicists have probably seen equations like this, and the first step is to put it into matrix form. And then solving the homogeneous equation, that is the equation without the force term, amounts to solving the characteristic equation for finding the eigenvalues and vectors of this matrix. So if we set the determinant equal to 0, go through the algebra, you can find a homogeneous solution that describes this behavior. So the current will then be a linear combination of the two eigenvectors with complex exponentials, where this lambda is the eigenvalue of this matrix. Again, complex because the imaginary part gives rise to oscillations and the real part gives rise to decaying exponential. So here, if you were to plot the two currents together, you would find that they both oscillate, but that their energy is kind of sloshed back and forth between the systems as they induce currents in each other. So as you can see, both of them kind of eventually dissipate their energy into that's the decay rate I was talking about. Of course, this also doesn't describe the forcing term. So the forcing term, the job of that is to keep this whole thing going. Now we're talking about LC circuits, which means that each of them has a characteristic frequency called the resonance, called the resonant frequency, which is related to the inductance and capacitance. And if you want to get any sort of reasonable energy transfer, you better meet that frequency, or else it just doesn't work. So this is where the impedance from the inductor and capacitor are equal and opposite, and you can achieve large currents. In the case of MIT, this is about 9.9 megahertz. Once you've tuned the coils to be in resonance with each other, the efficiency is given by the total amount of work, the amount of work which is dispensed usefully into this gamma W, divided by the total amount of power in the system. Power that's usable and total power on the bottom. In the paper, they insist on using a relationship between the coupling and the decay rates to rewrite this in a slightly different way, which depends nicely on this ratio of decay widths expended into useful work and divided by the decay rate of the device coil. And then you take a derivative, set it equal to 0 to find when this efficiency is maximized, and it's given by this condition. All I'm trying to show here is this is what MIT is trying to achieve in their setup. So now a little bit more about this actual coil. So this came as a surprise to me, that it's an open-ended coil. How does this work? They actually said, to the best of our knowledge, there is no exact solution for a finite helix in the literature. So there is still research to be done in electromagnetism, believe it or not, and they went and developed a little theory for how this thing oscillates. So you can imagine pushing charge, say from this point, pushing it down until it reaches this point. You'll kind of be building up an electrostatic spring, which, when you let it go, will convert into magnetic energy as the current rushes back in the other direction, which will then overshoot and charge the other side. And so this not only looks like a slinky, which is a mechanical spring, it also acts like an electromagnetic spring. So if we stretch it out, this parameter S, measuring the distance along the coil, we can then imagine how the current and charge profile should look on this coil. The current profile should be 0 at the endpoint because there's nowhere for it to go. And the charge, as we imagined, will have extrema on the opposite ends. So this is the basis they use, and also remembering that this whole thing oscillates in time. So we'll have a corresponding inductance, but also a built-in capacitance, which you can calculate with these very Jackson-like formulas. I haven't bothered to do that, but this is the model. The resistance is quite interesting because it comes in two parts. First, there's an ohmic term which is related to the conductivity sigma of the conductor. And there's also a radiation term which describes the energy that decouples and goes to Mars. This is related, this has two parts. Can you see that? It's a little bit dim actually on the screen. Hope it's okay. It has a magnetic dipole radiation term, but also an electric dipole radiation term. And the goal of this, or one of the goals, is that we can now describe the decay rate which is intrinsic in this oscillator, which will be related to the total resistance on top, both ohmic and radiative, as well as the inductance on the bottom. With similar arguments, they were able to derive a relationship for a theoretical prediction for how kappa, the coupling, should change with time. That's shown here. So here, there's nothing really exciting. You would expect that the further you pull the coils apart, the more they decouple. So this coupling constant decreases. So for instance, at 2 meters, it has this value. But it's nice to see that there is a good agreement between theory and experiment here. By the way, that's the formula for the coefficient, coupling coefficient. It is linearly dependent on the mutual inductance M. This is the more interesting plot. This is the efficiency of this transfer as a function of distance. So as you can see, when you're really close together, the efficiency is quite large. And the theoretical curve can be deduced from that formula I put on the board for the maximum efficiency. So for instance, at 2 meters, again, now we have actually measured in the experiment over 50% efficiency. So this was, it doesn't seem like a lot, I guess, depending on how you look at it, but this really did mark a very important progress in the field of wireless power transfer, and led to various other papers, a second of which I will consider now. So the previous one was published close to 10 years ago, in 2007. This one, wireless power transfer based on magnetic quadrupole coupling in dielectric resonators, published by these folks here, who I'll call authors number 2. They are based out of St. Petersburg, and they published their results in Applied Physics Letters in January 2016. So that's this year. How does it work? We have proposed and demonstrated experimentally an original approach to magnetic resonance wireless power transfer system based on high refractive index dielectric resonators. I think there's a typo in there, but it's word for word from the paper. This is how their setup looks. Pretty simple, right? You got 2 little spheres, radius 1 centimeter, and these are what before was the source resonator, the oscillator that they use to excite the coil. So it's similar actually in setup, except that there's none of these coils that MIT was using. They use spheres instead. And of course the distance scale is quite a bit smaller. But the frequency is also higher, so it equates. These things are made of this really funky material, Balntio, and it has a relative permittivity of 80, so the speed of light is about 9 times slower in this medium. But how does it actually work? Like, when I first saw it, I thought of these spheres. Like, I know how coils can give energy back and forth, but spheres. So the operational principle of the proposed wireless power transfer system is based on the Me theory, i.e., under a proper excitation, a high refractive index dielectric sphere exhibits very strong magnetic resonances. This was something new to me, and their illustration here was very helpful. So if you imagine applying an external field onto this dielectric body, the charges, the bound charges inside will respond in such a way that could vary with time. If you push it with just the right frequency, they could go back and forth. And it has certain frequencies and certain modes that it prefers based on its geometry and its electric properties. So you can imagine in the magnetic dipole mode, exciting a mode of the magnetic field, which looks like a dipole, and also in the quadrupole mode, exciting a magnetic field, which looks like 2 bar magnets facing each other. And these oscillate back and forth with characteristic frequencies, natural frequencies. The problem of solving this sort of situation, of analyzing this sort of situation, starts by listing Maxwell's equations for this medium, and in the absence of free charges and free currents, this leads to 3D vector wave equations for both the electric and magnetic fields. And if we consider this very plain e to the I omega t dependence in time, we can write the right-hand side of the equation as just negative k squared e, whereas the left-hand side, the Laplacian, gets split into its radial and angular parts in spherical coordinates. This is known as the Helmholtz equation. It simply says the Laplacian of the electric field is equal to an eigenvalue times the electric field, where here, L equals to r cross grad is the angular momentum operator. And someone get that? I'm sure you're all very familiar with this from quantum mechanics. So if we want to find an eigensolution to this equation so we can build up any sort of incident fields, it turns out it's much easier to look for a solution of the form position vector dotted into the electric field. This is just how this equation rolls. And so it's easy to find this solution to the equation. R dot E Lm, so just one of the eigensolutions, is equal to the product of three different eigenfunctions. The first is what we call the Henkel functions. This is just someone wanted to get their name out in science, so they decided to name a linear combination of the two types of spherical Bessel functions after themselves. It's just a really nice way to define them in such a way that's quite general. Oh, so by the way, the Henkel functions solve the radial part of the equation. The spherical harmonics are eigenfunctions of the angular momentum operator, as you know, and they look like these jukes here. And the third eigenfunction is the one we already looked at, which is an eigenfunction of the second order time derivative. Okay, I'm going to go through this quickly. We haven't actually solved for the electric field. We have R dotted into the electric field. But to get at the field itself, it's not too bad. We can use Faraday's rearranged and then substitute in the curl of the magnetic field instead of the electric field, with some help from the eigenvalue relationship for the YLMs. That whole thing will give us actually the magnetic field, which in place of the R dot, we now have an angular momentum operator sitting in there. In any case, I wanted to show you a little bit of the mathematics because in the paper there is none. They just say this is me theory, so I wanted to look that up. So this describes how a dielectric sphere responds to an incident field. The key thing here is that, I guess you can't see it so well here, but we looked at this relation. So here we have a eigenvalue equation, right? So k squared is going to be quantized. So k squared can only take on values that are consistent with the eigenvalues that these operators like to pick. And in that sense, we will have certain modes appearing out of this. Certain frequencies which correspond to resonant modes. So this is a plot from the paper which shows the reflection coefficient shown both theoretically and experimentally for the sphere. Basically shows you there are different modes where the sphere becomes more susceptible to the external field coming inside of it. These correspond to the dipole, quadrupole, sextupole, and octupole modes. And you can see that as the mode order gets higher, the quality factor increases. So here, this is a log scale, quality factor meaning the undampedness of these oscillations, how free they are, goes up so that the quadrupole mode is about an order of magnitude larger than the dipole mode. Now in this paper, they considered exciting the sphere at both the dipole and quadrupole frequencies. They realized that if they do it at the quadrupole frequency shown in the green curve here, they can actually beat MIT. This is MIT's results using the coils. So this is a very remarkable find, quite exciting that you can use these little spheres. The dipole mode is not so great, but nonetheless. And notice the scale here. This is distance divided by lambda. So they've normalized for the fact that we're using different frequencies, right? Here's a closer look at those efficiencies. On the left, we have the dipole efficiency. On the right, we have the quadrupole efficiency. Here, you can see that the quadrupole one does better, reaching about 80% efficiency at this about, 0.05 distance divided by wavelength. Another important thing that they discovered is that this setup is more robust in terms of its angular dependence. So if you can imagine a commercial application of this, you wouldn't want to care about how you're oriented with respect to the source, right? You would want to be able to have good efficiency no matter how you spun around. So the quadrupole mode in green is most robust to changing the angle. This is both measured and simulated. They have found the same trend. The dipole one is terrible. It goes to 0 as you move the source and device from being fully aligned to fully perpendicular. So this just has to do with how the fields are oriented in space. Okay, that sums up the second paper. Again, very important result. There's a new flood of interest now in this new kind of way of achieving wireless power transfer. So I'm excited to see where this goes in the next few years. Perhaps one day, not long from now, a typical living room will have this kind of source coil, and we wouldn't need the USB cables. Apparently, this is going to be the new cell phones then too. Looking forward to that. And yeah, so this would be great. And this kind of an effort is being led by the MIT people, the MIT authors. Here you can see them standing in the direct path of their wireless power transfer, which leads me to an interesting point. They notice that the efficiency of the transfer is not very much affected by putting things in between, like humans. And one might wonder not so much how the efficiency depends on the humans in the path, but how the wireless power transfer affects the humans in the path. So they notice that at distances 20 centimeters away from the device coil, the power radiated for these parameters is 5 watts, which is roughly an order of magnitude higher than cell phones. So if people are concerned about cell phone radiation, then probably we're going to have to do a little bit more research on the possible health effects of this radiant transfer before we fill our house and living room and living space with these oscillating magnetic fields. Nonetheless, there are already startup companies, one of which called Ytricity, is seeking to find solutions for wireless charging in the everyday. They even have like a cart, like you can start buying things already. I don't know if they have any devices, but I think this was founded by one of the MIT guys. So it's out there, and here's another example I found called Plugless, which provides solutions for wireless charging of electric vehicles. So I don't know how tedious it is to charge an electric vehicle with a plug, but apparently enough to give these people, a market. And they also have a card, so I haven't bought anything, as you can see. But nonetheless, so I'm not sure how fast this technology will pick up, but I'm sure that in the next few years, these papers will be important in any sort of new advances in this field, as we start seeing this maybe take grip and become more common in our society. Mind you, not as huge as Tesla had imagined, but who knows?
Some questions, right to the time.
Is it too fast? Yes, this one.
Yeah, I noticed it was strictly like a peak in the efficiency that wasn't at 0 for the quadrupole moment.
For the angular dependence?
Not the angular, actually. The distance.
Right, yes. Yeah, that's really interesting. I was looking at that too. So right here, you find that at the peak of the efficiency is not at like the closest you can get them. I guess this just has to do with how the field is distributed radially. If you look at those Henkel functions, you will see that perhaps for the second order mode, the Henkel function has its maximum a little bit further away from the origin. Whereas the first mode, the dipole mode, probably the maximum is at the origin. That's a good observation. There's another, yeah, David.
So for efficiency, was there anything in there that has to do with like how big your resonator is? Does that impact the efficiency? Like the spheres are small,
yeah.
The MIT ones are big.
Yes, there are a few things. You notice that the quality factor depends on omega, the angular frequency, and the angular frequency depends directly with the size of the resonator, because you can fit more modes in there, and you would lower the frequency of, say, the dipole mode if you make the resonator bigger. It's just a boundary value problem. So they would like to bring the frequency down, if I recall. I can't remember why they said that. I think for radiative losses. If you remember, the radiative losses depend on the angular momentum also. Oh dear. Anyways, the radiative resistance had this term depending on omega as well. So yeah, I guess quality factor goes up with omega, but also does resistance. So there's probably some sweet spot in there. Yeah, but you can change the frequency this thing operates at by changing the size. They said that they could only get samples 1 centimeter in radius. So I don't know why, but it's all they had to work with.
Questions? Comments? Blanks? Not then, let's think.